Okay, here we are in a brand new video, and I represent this left-hand side. It's what this is all about. It's a diagram that comes out of a textbook. It's from Mathematics for Engineers, 1926, and it was by Raymond and Robert Dull, or by Dull and Dull, and it's published by McGraw-Hill. Okay, so let's see what all I did to this diagram was to mathematically model it to be interactive and to be for the purposes of intuition. And so let's see what that looks like. Here's an angle control. Okay, the angle has moved. Let's move it again. Now, since this is a mathematical modeling, a correct mathematical modeling, each and every one of these line segments is recalculated and redisplayed in real time. And according to the mathematical relationship as you see them, here is quantity A, and here's that same quantity to the second power. In other words, A to the first power, and then that same quantity A to the second power. Over here we see a quantity B to the first power, and we see that same quantity to the second power. And over here we see, since the hypotenuse is 1, this is inside of a unit circle. This triangle is inscribed inside of a unit circle. Then the hypotenuse has a value of 1, and since it's an A, B, C right triangle, and since C equals 1, C squared equals 1. Okay, so as an aside, the neat thing about using letters for symbolic values is that they can at the same time be useful in terms of naming the sides, A, B, C, and they can also at the same time be useful in terms of showing the mathematical relationship between consecutive sides. Let me get a better angle here. Okay, so here we see the mathematical relationship between this black line segment and this green line segment. They're consecutive powers of the quantity of A. So the quantity of A here is to the first power, and the quantity of A here is to the second power. And here the quantity of B is to the first power, and the quantity of B is to the second power. It shows, so we're leveraging this whole concept of symbolic labels. Not only does B squared represent the name of this, but at the same time it represents the mathematical relationship between, well, B to the second power and B to the first power. That is pretty neat. Let's keep track of that. Okay, so as another side, I like to think of, there's something very interesting going on with the hypotenuse here. We see it seems to be quite literally saying the quantity A squared plus the quantity B squared is equal to C, or 1 or C squared. So if C equals 1, then certainly C squared equals 1. As an aside, I like to think of what's going on the hypotenuse as being, well, two numbers that always add 1. Well, I've learned a new term. It's called invariance. So I'm going to try to use that term to represent what's going on here with this hypotenuse. In other words, I like to think of this as this term here in the Pythagorean theorem, and this term here in the Pythagorean theorem. They're added in the Pythagorean theorem. It's kind of like we get two quantities that invariantly add to 1. In other words, they invariantly, always the sum is invariantly equal to 1. Okay, so as another aside, I sort of like to think of this relationship here as being two collinear components of unity. And over here, as another side, I like to think of A and B as being two components of unity. They add to give you 1 always, but in in a different kind of way. They added a 90-degree angle. And there's another term for 90-degree angle. It's called orthogonal. So I like to think of A and B as orthogonal components of unity, and A squared and B squared as being collinear components of unity. Okay, so before I want to move on, I want to make mention of one thing. This approach that you're about to see here in just a minute is based on similar triangles. I've seen other people do a similar triangle approach, but they never used the unit circle. They never used what I like to think of it as a unit triangle because it has a unit hypotenuse. In other words, a hypotenuse of length of 1. If these other people that I'm thinking about had used a unit triangle, or a triangle with a hypotenuse of 1, they would come up with the exact same results that you see in this diagram. In other words, using a hypotenuse of 1 has revealed this geometric relationship between these two components of the hypotenuse. I want to represent that if you did not use a unit hypotenuse or a hypotenuse of 1, then this result, this geometric result of A squared plus B squared, would be completely obscured, and you wouldn't see it. So anyway, that's the difference between that's the difference that I wanted to point out between using similar triangles and using similar triangles within the context of a unit circle. Okay, so moving on, we have 2 lines of proof. This gives you the A squared proof. It's just one line. And here, this one line here gives you the reason for B squared, the B squared line segment. Just two lines of proof. Unbelievable. So I want to represent that the act of putting this altitude here to the hypotenuse as a base has resulted in 3 things. It's resulted in getting 2 more triangles, and they're all similar. So we have 3 similar triangles. That always is true for putting an altitude into a hypotenuse. And if you want to pause, you can go through that until you're familiar with that. But for the purposes of trying to keep this under 10 minutes, I'm going to let you pause and then, okay, come back. The second neat thing that's going on with this is that take a look at this side right here. Take a look at what's going on with this side. It's the hypotenuse of this smallest triangle. At the same time, it's the opposite side of this largest triangle. So it has a dual role. In a ratio and proportion, from a numeric point of view, that has a very interesting result. Notice how this is blue color-coded here, and this line segment is E, and this line segment is B. The relationship of the opposite side to the hypotenuse is E over B, and we see that right here. For the small triangle, the ratio of the opposite side of the hypotenuse is E over B. Okay, for the large triangle, the same corresponding sides, opposite over hypotenuse for the large triangle, are B over C. Okay, so let's see what that looks like. Opposite side is B for the large triangle, and the hypotenuse is C, or 1. Okay, so we can see that cross multiplying here, it gives us this magic. That's where the B squared term, the second power term, comes from, because this side that serves 2 separate roles. One role is the opposite side of the large triangle, and the other role is that it's the hypotenuse. It's the hypotenuse of the small triangle. So when we cross multiply, we get our second power term is equal to E. These being equal, You can see that I put that there. Isn't that pretty neat? That is really neat. That's a byproduct and a direct result of putting this altitude into this hypotenuse, but only in the context of a unit circle or a unit hypotenuse or a hypotenuse of equal to 1. Okay, so moving on. We see the third thing, I said there was 3 things that happen here. The third thing is that this side, take a look at what's going on with this side right here. It's serving a dual role as well. The first thing is that it's the adjacent side of the large triangle, the original triangle, but it's also the hypotenuse of this medium-sized triangle. Okay, and we see that here. The adjacent, so for the ratio of the adjacent side of the hypotenuse of the large triangle and the corresponding sides, same corresponding sides adjacent to hypotenuse for the medium-sized triangle, we get adjacent to hypotenuse for the large is the adjacent side is here, that's A, and the hypotenuse is C, okay, A over C, and the adjacent side over the hypotenuse for the medium-sized triangle. Well, for the medium-sized triangle, here's the adjacent side right here, and here's the hypotenuse of the medium-sized triangle. Okay, so that's D over A. Here's D over A. So here again, we see that A is playing 2 roles. This is the same line segment here. A is the same line segment, but here it's playing the role of an adjacent side, and here it's playing the role of the hypotenuse. So that's the reason why we get a second power term equal D, and that's the reason why that's there. Okay. So anyway, as an aside, here's what we're trying to prove. A squared plus B squared equals C squared. If you reverse A squared, you get A times A, and B times B, and C times C. Here we see we have this really neat relationship. A can be used as for the purposes of naming something. But you can also see that how convenient it is when you think of it as a combined name and a symbolic value, because as a symbolic value, all of a sudden you can show the mathematical relationship between A and A to the second power. Here we're multiplying 2 symbolic values. Here we're adding symbolic values. Here we're raising symbolic values to powers. Here we're using symbolic values in equations. Anytime you have an equal sign, you have an equation. So I like to think of Pythagorean theorem as a Pythagorean equation also. So anyway, as another aside, if one of these components was 1/3, the other one would have to be 2/3, because they invariantly add to 1. And the neat thing about that is, for every decimal place into infinity, the relationship between decimal places in both terms is that they have to add to 9/10, 9/100, 9,000, 9/10,000, so on and so on and so on and so forth. Well, the same thing happens with, say, like if you had sine of 27 degrees. Well, this would be like B, and this would be like A, and this would be like B squared, and this would be like A squared. So this number squared is this number, and this number squared is this number. And oh, take a look, digit for digit they add to 9. 9/10, 9/100, 9,000, 9/10,000, etc., 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 all the way into infinity. So this is a very neat relationship that I just wanted to sort of add into the mix here. And anyway, that's the end of this video. Please like and subscribe. I hope you like this. Thank you. Bye.